Hey kids, welcome to our logistic curve lesson. Start with this warm up. This sub should have given you a copy of a couple of different things. This being the warm up going through a slope field, um, which isn't new, but this type of differential equation is going to be important to us today. Notice that it is, I've got y's on the wrong side. I can get y's over to the other side. It is separable, but it would take partial fractions to after I separate it because of this, um, the setup of this. So fortunately, you are not asked to do that. You are just asked to sketch possible solutions through the 0.32 and 0.8. And what we're hoping that you realize is that as you start here, that your slope lines to the left indicate that you have negative slopes and that your original function is decreasing. And then that you reach this kind of asymptotic behavior here. Notice that I look kind of exponential, but I'm, right, swoosh sliding, right? Where I'm coming down and approaching this asymptotic behavior, which is, look what happens here with my initial condition here, right? If I go to the left of my initial condition, my slopes are positive. Looks like I should be, right, increasing to this point, still increasing, but my slopes are getting a little bit steeper, right, here. But then my slopes start to decrease, though still staying positive, but I approach this same asymptotic behavior here, right? So whether my initial condition was above that asymptotic behavior, it looks to be at y equals 6, or below the asymptotic behavior, both ways I still approach that asymptote, once from above, once from below. That's going to be important to us today. All right, let's go on. So, exponential growth, what we've done in the prior lessons, where we had yect, right? I either have population growth over time, population decay over time. Also, approaching asymptotic behavior, right? Here's growth down here, a picture of exponential growth, right? So, as we said yesterday, this exponential growth occurs when your rate, the derivative, is proportional to the amount present. I said the derivative then of your population, y, with respect to time, is proportional to the population itself. Then, of course, using p to represent the population, this is what we have, right? But as time approaches infinity, this model suggests that the population grows without bound. That's not really realistic, right? There's limiting factors. If your bacteria is in a petri dish, well, you can only have bacteria grow to the amount of living space. Same with like a wildlife in a preserve, right? You only have so much living space. People, right? There's living space for people. There's, of course, infection. There's disease. So we're going to talk about a space having a maximum population or a carrying capacity, and we're going to call that carrying capacity M. And excuse, we are traveling. Mr. Getz and I are traveling. Say hi, Mr. Getz.
Hi, Mr. Getz.
Ha so excuse the car sounds. Anyway, logistic growth model says that your growth rate is proportional both to the amount present, so you still have the KP situation, but then you have another factor that is a fraction of the carrying capacity that remains. So having dp dt is equal to kp, there's my exponential model, but we're now saying we want to multiply that by a fraction of, hey, I have a population, we've used some resources, maybe there's been some disease introduced or a predator introduced, How can I mathematically account for that here? So let's just suppose, to figure out what we should multiply by, let's just suppose our maximum carrying capacity is 100. Look at this fraction. If I have 1 minus a fraction of my carrying capacity, 1 being the whole, if you have a very small population, so let's say I have only if my carrying capacity is 100 and I only have 10 people, bighorn sheep, bacteria, whatever it is, the ratio of that small population to 100 is a relatively small fraction, right? This would be a small fraction. So 1 minus a small number would still be close to 1. And if you multiply ky over here, or kp times something close to 1, you'd still have something very close to your exponential growth, right? However, what happens if you're very close to your carrying capacity? So let's say you're 99 over 100. Then 1 minus 99 over 100 would be something pretty close to 0, right? This number, if you have, as opposed to just having 1 up here, let's say make it even smaller, I only have 1 person out of 100, and I'm allowed to have 100. Here I have 99 when my carrying capacity is 100. 1 minus a fraction very close to 1 is going to be close to 0, which is going to take this multiplying ky is going to have an effect, and it's going to slow this exponential swoosh down. Still going to be positive, so you're still going to be growing, but you're going to slow it down. So here's what that looks like. You still have your k times p. There's your exponential swoosh, but you're going to multiply it times 1, the whole, minus how much of the maximum carrying capacity have you used up. And that'll slow your growth down. So here's what the curve looks like. Do you see the exponential growth at the beginning? Right? Here's your slide swoosh right here. But then this factor starts to slow the growth down, and you reach a limit of the carrying capacity. How quickly you get to the carrying capacity depends upon this fraction. Right? So here's the carrying capacity. We call that M. And the limit as time goes to infinity of your actual population equation, right? The graph, not the derivative, the graph will always be what? M, right? Instead of your exponential growth model, right? What's the limit as x approaches, as t approaches, let me put it up here. What's the limit as t approaches infinity of your exponential model? That's infinity, right? Well, again, that's not realistic for models. You're going to have some kind of slowing of growth. So you need to slow your roll, right? And the logistic growth model does that. And then look at the point of inflection. The point of inflection at some time here, at some time, at the point of inflection, the population shows its maximum rate of change, right? And slope-wise, that's the steepest slope there is at the point of inflection, where the exponential growth slows to a logistic growth. So my logistic differential equation can be written this way, right? Where you have the factor multiplying to slow the growth. But I can do some algebra on that and make the equation look that way. Do you see what I did? right? I just got a common denominator. I made this m over m, and then m minus p over m. Here's what it looks like. Also, since this is all multiplications, I could float that division by m outside and make it look like that. So these, the reason I took the time to show this is because, one of the things AP tests you on is just recognizing the logistics differential equation. Sometimes they present it in, most often I've seen it presented in either this or this form. Okay, and I'll give you some examples like that on a handout. So speaking of the handout, the sub should have classwork handout where the front of it is some multiple choice. So look at this. Let K be a positive constant. Which of the following is a logistic differential equation? So hopefully you can eliminate this right away. This is exponential, right? This isn't even, oh, I'm sorry, this isn't even exponential. This is linear. Do you see why? Ha, why? This is a linear differential equation, right? Because when you anti-differentiate that with respect to t, you're going to get, right, your variables math. You're just going to get your quadratic. But here's your exponential, right? You got to separate your variables. You're going to get ln y. You're going to e to the, there's your exponential. This looks like logistic, is it? No, because you have a t over here. This looks logistic. I have ky. Oh, but I have 1 minus t. That's no good. So I've eliminated all of these. So if you look up here, E matches, right? It's the rate of change of y with respect to t is equal to ky times a factor that considers how much of your carrying capacity you have used. By the by, what's my m in that equation down there? Yeah, m is equal to 1. Small carrying capacity, right? How about the next one? If you want to pause the video and wait, see if you can do these on yourself. That's a lot of words, but all you're doing is matching to a logistic differential equation. Highlight these words, though, up here, because you might need these later, right? Jointly proportional. That's how you tell the difference between that and when it says just proportional to for our exponential growth. Jointly proportional to the size of the rabbit population and the difference between the rabbit population and the carrying capacity, right? So that's this in words, right? The difference between the carrying capacity and the population, right? They've manipulated this equation to this one. So which one of these choices do you think it is? Can you see the 2400, right? So the 2400 is in each one. This one doesn't have minus p, so hopefully that one's out. But can you decide which one of these it is? Doesn't quite look like any of them yet, unless you realize, oh, wait a second, maybe actually I should be looking at this form. What happens if you divide everybody here by 2400? Don't you get kp over 2400 times 1 minus p over 2400, right? dp dt. So D is that answer as well. One more of these before we go into some more. Right, so again, all I'm doing really is just all they're asking me to do, and these were questions on the AP, is right, identify the differential logistic equation. Here we have a number of moose modeled by a function satisfies the logistic differential equation. So this time they just said that straight up. You have a logistic differential equation and they're giving it to us. Do you see the form? Right, K is 6 over 10. Annoyingly, right, they're using, instead of P, they're using M as their population number for moose, right? M is not your carrying capacity. What is your carrying capacity, by the way, in this form? Yeah, 200. So what we call M, the carrying capacity, is 200. And it's asking you a limit question. Given that the initial condition is 50, if I have a logistic differential equation, here's 0, 50. I already know the shape of the solution. Shape is going to look like that. There's a logistic curve with a point of inflection there. And I'm going to have a upper bound, a ceiling. Where's that upper bound going to be? At my carrying capacity, right? So what is the limit as t goes to infinity? Carrying capacity. Done. Right? Sweet. So these are the kind of multiple choice questions that you can get done in 2 seconds if you realize what they're asking you. Right? All the ones that we've done so far would be very quick multiple choice, but unaccessible if you don't know what they're asking. All right. So look at the warm up. The warm up, right? Go back and look at your warm up, was a logistic curve, right? A logistic slope field. And look at this differential equation, right? Can you see the K 1/8 times Y is equal to 6 minus Y? So this is the K, right? Y, one minus Y, if you will, right? So what have they've divided through by? So can you see that 6 is there, right? We're in the M minus P version, so my carrying capacity is M. And look at what we have right here. So if your carrying capacity is 6, but your initial condition over here is 0.8, you've started with too much population, and your population over time is going to decrease to 6, as opposed to if you start with an initial population of only 2, well, I guess that's not initial, but at time equals 3, your population is 2, you still have some room to grow, but you will grow, your population will grow, and then the growth will slow until it levels out at 6. Again, as opposed to 8, you're over your carrying capacity. Your environment cannot sustain that, and so the population will decrease and level out at 6. Cool, right? So here is your logistic differential equation in one of the forms. Remember, you have other forms as well. When you move this M over here, you have Kp is 1 minus P over M. And then the solution that I can get with separable differential equations and partial fractions, I can get this logistic model. Notice how different it looks from Yecht, right? But here is your carrying capacity. This is not your initial condition. Kids get that mixed up sometimes. I have to solve for A and I have to solve for K. And A is not your initial condition. And I'll explain a little bit what A is conceptually when we go through a problem. Some people still call this C, so I have seen this written in some books as M over 1 plus C e to the negative kt, right? As long as you understand that that C is not the initial condition. This has a nice little, you can write, this kind of looks like mice. Do you see it? M-I-C-E. Again, more important to me is that you understand that that C value is not your initial condition, or that A value, whatever you call it, is not an initial condition like it is for YECT. Your book confusingly uses another form of this where they kept the M out of the denominator here, and then it shows up in the denominator of the model. I've seen it doesn't matter what you use, I swear the math comes out the same, I promise. But I just wanted you to be aware, if you're looking at your textbook, that I haven't made a mistake with this, right? It really is the same equation, just algebraic manipulation of the two. So on the back of your classwork handout is where I have this example of 10 grizzly bears. So they're introducing 10 years ago is when bears were introduced. They were initially 23 bears. The park can support a maximum of 100 bears. So there's your carrying capacity. Assuming a logistic growth model applies, find a formula for the population as a function of time. You do not have to solve that logistic equation. You just have to remember the formula, right? So whether you remember it this way or you remember it as mice, doesn't matter as long as you are able to fill in the appropriate information. M is 100. My initial population was 10. That is not A, but I'm going to use it to find A. And I'm also going to use the point that at 10 years later, there were 23 bears, so I did have population growth. So the first thing I'm going to do is plug in 0 for t, which is nice because I get e to the 0, which is 1. Do some algebra. And look at that. This will always be so, right? Can you see what happened here? 10 was my initial population, right? Is equal to m, my 100, over 1 plus a. That will always happen because you're plugging in 0 for t, for your initial population. So that's a formula that you can solve for a if you want. So if you want to know a straight off the bat, it is always the maximum comparison capacity minus the initial population divided by the initial population. The meaning of it, if you can interpret that, is it's basically how many groups of A will fit into your carrying capacity. So look at what we do with the algebra. Solve here. A is 9. 9 groups of my initial population would fit into my carrying capacity. But it is not the initial condition, right? How many more groups, I should say, right? Because I already had 10. So doesn't that make sense? If your initial population was 10, how many more groups of your initial population can you put into your carrying capacity? 9 more, right? 9 times 10 being 90, added to the 10 that you already had. So that's the interpretation of what A is. Now I got to go solve for K. So I'm going to use my second point. And this is where you need your calculator for this, right? I actually don't write a lot of this math down when I'm doing this problem, right? I don't need to write down all of these steps because I have a calculator in my hand. So I'll show you what I usually write down when I have to do this, right? I certainly find my A, right? And then I show that I've plugged in this. And then I do this work on the side, right? I may do my reciprocation, right? I don't need to show that I've actually subtracted 1 from both sides, right? Which is really negative 23 minus 23 over 23. That's how I got rid of the 1, right? Then I divided by 9. Then I took the ln, right? At this step, I pretty much would pop from here over to here, right? Is all that I would write down. Then on my calculator, I would store this in alpha A, or if you're cute, in alpha K. And notice when I write the equation down, this is not my final answer, so I didn't have to write 3 decimal places down. But if you are asked for a final answer, I would write this. My equation was my final answer. I would write this down, KT, and I would highlight this to 3 places past the decimal. Or you could write 3 places past the decimal right here, either way. So put this into y1, put this equation into y1, and be careful that you do 1 in your calculator, you do 1 divided by parentheses, all this stuff, right? So I'm going to put this into y1, and I'm going to graph it. I'm going to choose my window to go to at least 100, my y max to go to at least 100 so that I can get my picture on. And I see my logistic S-looking curve. So B says using your model, predict. Again, you have a calculator in your hand. Do not do a lot of math. Plug in 50. Plug in 75. And then use your calculator. And in Y2, graph Y equals 50. And in Y3, graph Y equals 75. And use intersection to find your answer. I rounded to the whole year. Don't do that unless they tell you to. Use, right, 3 places past the decimal. But often in these times they'll say, round to the nearest whole there, or something like that. But don't do that unless they tell you. And then look at C. Evaluate the limit as you go to infinity below carrying capacity. All right, please put a star next to this question. AP loves this question. So, when is the rate of the population increasing the fastest? What does that mean? The rate increasing the fastest. So, the rate, remember dp dt was the rate, right? That was our logistic equation. What is our logistic equation? You solved for k, didn't you? You know k is that negative 0.1. So you know k and you know m, right? M is 100. So that's our derivative. Our derivative, do you agree that the derivative is always positive because the S curve is always increasing, right? But they want to know when is the derivative. They want to know the maximum of the derivative. Can you see the maximum of the derivative on this graph? When is the value of your slope the highest? It's at poi, right? This is asking you for the point of inflection. The point of inflection is where the first derivative is at a max. It's also where the second derivative is equal to what? Yes, 0. So here's our first derivative, right? With my k and my m put in, I'm going to distribute. Well, I'm going to mark my poi, right? Changing from concave up to concave down on the original is where the first derivative has a max and where the second derivative changes from positive to negative, OMG. You find that by setting the second derivative equal to 0. Now, you could also put the first derivative in your calculator and find the maximum of it, but you have to write down the second derivative. I told you this, right? You can never find a max and min with a calculator. Even though you can't write that down. So here's me doing the distributing to get the first derivative. The first derivative is positive on 0 to 100, right? You can see that. all positive slopes. There's me doing the second derivative, right? How did I get that? I'll show you, right? I said we're doing the second derivative. I got 0.1p minus 0.002 p dp dt. The chain rule is always in play. And then I factored out, oops, sorry, I forgot my dp dt here. dp dt minus, right? Your variable doesn't match. You must spit out the derivative of p every time you differentiate. Then I factored out dp dt, and I got this expression. Remember, dp dt is always positive. See that? The first derivative is always positive. So the only thing for the second derivative being equal to 0, the only thing I need is to find out where this factor is equal to 0. So when is 0.1 equal to 0.002p? P is equal to 0.1 divided by 0.002, and that turns out to be 50. Right? dp dt was always positive. I took 0.1, found out that it was 0 at p. I already know the second derivative is going to change from concave up to concave. The original change from concave up to concave down. So I know at p equals 50 is the y value, right? This is the population of bears. So at 50, does that make sense? Look, that's where poi is. That's 50. Didn't we already on the previous slide find out what p-value that was at using our calculator, right? Didn't we do that? We got 22 something years because they asked when. So when p is equal to 50. So I got my calculator. Again, I showed that I put 50 equal to that to p of t, but on my calculator I used the intersect function. Right? And we already did that. We got 22 point something years. Now, it would be swell if I didn't have to do this work every time. There is a pattern. The y coordinate of the point of inflection was 50. What was your maximum carrying capacity? Yeah, I can do this math up here in the abstract with just m and show you that for every logistic curve, m divided by 2, your carrying capacity divided by 2 will always be the y coordinate of the point of inflection. So if they only ask you for the y coordinate, your math is done. Carrying capacity divided by 2. It's if they watch out for the when. If they ask you when the rate of change is the fastest, that's when you have to use intersection and set that m over 2 equal to your solution. So look, your homework, this is your homework, the sub should have passed out to you. I wanted to go over number 1 with you first because it has a little bit of a twist. And then there are going to be times in your homework where all you have to answer is m over 2. Right? This is not an m over 2 question, but it is a nice little twist on the don't just you have to recognize the differential equation and set up some algebra. So the rate of change of the number of people on an ancient beach modeled by Logistic. The maximum number of people on the beach is 1,200. So there's your carrying capacity, right? At a particular time, the number of the people on the beach is 200. So the function I don't see yet, p of 200, I'm sorry, P of 10 is 200. At that time, the number of the people on the beach is increasing at a rate of, what does that mean? Increasing at a rate of, which equation is that? That's not P, that's what? dP dt of 10 is what? 40. So which of the following differential equations describes the situation? Well, I hope you can see that's not true. Each one of these, the rest of them, has a 1200 minus P. So I think to myself, I probably am dealing with K over M P times M minus P. Right? What can you fill into this? Well, right now I can fill in the M, right? So let's do that. K over what? 1200 P times 1200 minus P is equal to dP dt. I need to know what that multiplier is. I need to know this, right? Well, I actually already know it's 1200, but this number, whatever number is the correct one, and remember I've already eliminated that one, that number is K over M. So one of these numbers is K over M, which we know for our problem is K over 1200. What can I do now from here? Oh, I know dP dt at a certain time, don't I? I know the rate of change is 40. Well, what do I care about that it's at 10 a.m.? How does that help? I don't have anywhere to put 10. How does that help? Oh, wait. You know the population then, don't you? Don't you know the population at that point? At 10 a.m.? What did they say? The number of the people on the beach is 200. So at P at 10 a.m. is 200. So here you can take this 200, not the 10, and put here. So what do I have? 40 equals K over 1200 times 200, because at 10 a.m. the rate of change is 40, but the people on the beach are 200, times 1200 minus 200. I do that math and get K by itself. So you're taking on your calculator 40 times 1200 divided by 200 times 1000. And I got K to be 12/5. I'm really happy. I go up here and I look at, oh, there's 2/5. Did I do something wrong? Do that math again. No, 12/5 is right. What the heck? Remember what we were looking for? This number is K over M. K has already been divided by 1200, right? So what is K over M? 12 over 5 times 1 over 1200. Do that on your calculator, math fraction that. If you can't see it, just by your reducing here, and that's 1 over 500, which is C. Oh my gosh. That problem took me a little bit of time. It took more than just recognizing the differential equation. So as you go through your homework, and when you look at, sometimes you are just asked to recognize. Number 2, just recognize. Number 3, what's the limiting value? That should be quick. Number 4 is very similar to the one that we just did. Number 5, maximum carrying capacity, quick. Number 6, similar to what we just did. Number 7, interesting question about interpreting the graph. Oops, sorry. And number 8 is where you're going to have to use your m divided by 2. Now I just realized that on my slides, I skipped a problem that was on your classwork. So let me go back to do that one. So I'm sorry about that. I went into a homework problem and forgot that I had this on the classwork. So on the classwork problem, this will help you with one of your homework. Classwork number 5 says I have a logistical equation, rate of change of something called n with respect to time is equal to that n over 10. This is in the 1 minus p over m form. So do you see what m is? M is equal to 850, right? So isn't that the answer to A? Right? Your carrying capacity is the limit as t goes to infinity of your S curve. Right? Here's 850. So then it says, when is the second derivative equal to 0? Second derivative equal to 0, what did we just find out? That is at 850 divided by 2, which is 425. Then it says, when n, the equation I don't see, when n is greater than 425, so when my population is greater than 425, is the first derivative positive or negative? The first derivative are your slopes, right? Your function is increasing. So your first derivative, right, n itself is increasing. The first derivative is positive. Therefore, dn over dt is positive, right? But what about the next one? When n is greater than 425, what's the second derivative? Well, n is still increasing, but concave which way? Down. Therefore, the second derivative is what? Negative. Right? That will help you with one of your homework problems as well. All right, so see what you can do with your homework problems. It looks like a lot. There's only a few questions that are involved that are like number 1, which is why I wanted to go through that with you. Hope you have a good day, and I will see you on Tuesday.